Hello, this is Out Loud by James Sinclair, the first puzzle in his Artisanal Sudoku Volume 111. It is a Sudoku with killer cages and German whisper lines. So let's look at the rules. Normal Sudoku rules apply, so place the digits 1 to 9 in every row, every column, and every 3x3 box. Killer cages. The sum of digits in cages is equal to the small number in the top left corner. So for example, those digits sum to 11, those digits sum to 10, and so on for every cage. German whispers along green lines. So these are green lines. Digits must differ from their neighbors by at least 5. So for example, if that digit was a 3, this digit could be 8 or 9 because those are at least 5 away from 3. But it couldn't be something like 6 or 7 or 1 or something like that. So yeah, those are the rules. With that, let us begin solving. So this puzzle is actually this puzzle was actually supposed to be colored. All the cages are colored like a light pink or something, but because we have German whisper lines which I intend to color, I have decided to I've just decided to remove the color for a bit so I can do some coloring. Yes, alright, so let's start with this 6 cage. What digits must go in the 6 cage? Well, the minimum we can put in a 3-cell cage are the digits 1 to 3, because they cannot repeat in the cage. Did I not say that? I think I forgot to say that. Yes, digits may not repeat in the cage. So something like this is not possible. But either way, what that means is this cage must have the digits 1, 2, 3 in them at least, which already sum to 6. So yeah, they have to just be 1, 2, and 3. What next? Right, let's look at the German whisper line in the cages specifically. We know that, well, how do I prove this? Along a line, digits must alternate in what is known as polarity, which is how high or low the number is. Because if you look at the number line, I'm just going to arbitrarily place digits here, which are not part of the solution, but if you look at the number line from 1 to 9, you realize there are 4 digits in front of the 5, and 4 digits after the 5. The digits below 5 are the low digits, the digits above 5 are the high digits, which get their own colors accordingly. And if you try and choose 2 digits that are differing by at least 5, you'll notice a few things. Firstly, you can't pick 5 because 5 itself cannot have any neighbors that are 5 away. Next, if you choose any numbers from one particular side, the next number you choose that is 5 away has to be from the other side. And so in your line, for any color of one cell, let's say it was blue, the colors next to it must be of the other color, and therefore you get this alternating pattern. And so from this 10 we can say that, well, those two have to be different from that, but we can also say something. Actually, I think the colors are wrong here. We can say that those two cannot both be highs because the minimum digits you can place for the 2 high digits are 6 and 7, which already add up to 13, so it doesn't work. They must both be low. And in fact, the same works here. Those 2 digits must be low because if they were both high, then they would already add up to at least 13, which means that digit has to be a 0 or less, which doesn't work. So those digits are low as well, which actually means we get the colors of all of these cells. So those are all low digits and those are all high digits. Alright, so what do we have? Well, that digit is high and those 2 digits are low. If both of those digits are at least a 3 because they're at least 1 and 2, then this digit is at most a 7 because it's 10 minus 3. So this is only 6 or 7. Not sure where I can use that though. I guess okay, in each row and each column and each box there are always 4 lows, 4 highs, and 1 5 in it, which means that all 4 highs are used in this row, and actually in each of these columns and rows they're all used up. So the outsides must have lows and 5s only. Does that do anything? it doesn't really say much because 2 lows work here, a low and a 5 also work here. I don't know. I guess those are all low digits because 1, 2, and 3 are low. How about this? Do they all have to be... No, because 4 can be with 7 and 9 to make 20. So they don't have to all be high. If they're all high, that would be useful, but they're not all high. In fact, if you added 6, 7, and 8, you get 21, I think. Which doesn't say anything still, honestly. Because the 21 cage can still have a 5 in it, I'm pretty sure. Yeah. Alright, well that is unfortunate. We don't have much to go off of right now. Maybe we still have coloring to do though. Because this forms a number of almost full sets of lows. Not really. Oh, I just realized this can't be 6. Right, because it's a German whisper line. Therefore, 6 cannot be with anything other than 1. And you can't put 1 in both of those cells. Which means it has to be 7, which has to be next to 1 and 2. That makes sense. Right, also, yes, another trick to use here is that 6 and 4 on a German whisper line can only have one partner. That is, if you try to find partners for 4, you can only have 9, and that's it. Same for 6, 6 you only have 1. And so, those digits, for example, cannot be 4, because those digits require 2 distinct neighbors. And so those digits can only be 1, 2, or 3, which forms a triple. Those digits are, well, 6. Yeah, 6 can't be here or there, so 6 must be here, which must be next to 1, which resolves this pair, which gives us a 3 here. Those digits are therefore 8 and 9, which we can't distinguish. So yeah, that's unfortunate. Right, and so 6 in here can't be in those cells, 6 must be there, which must be next to 1. And again, 4 can't be in those cells, so they must only be 2 and 3. Those cells, well, this could be 4. But this can't be 4 either. In fact, those can't be 4. So those are 1, 2, or 3. This forms a triple here, so that's useful. This digit is not 1, so it's 2, 3, or 4. What is that digit? Well, I guess at maximum you can have a 5 in here if you use 2 and 3. So this is at most an 8. So I guess it's a 7 or an 8, because it can't be 6. Yeah. Actually, can 7? No. Wait, 7? Does 7 work? No, sorry, it has to be higher. Sorry. Because it's at most a 5, this is at least an 8. And in fact, if it was an 8, it would need to be 2, 3. If it was a 9, it would need to be 1, 3, right? To make 4. Yeah. So that tells us 7 must go somewhere. But 7 can't be here, because 7 here would be pushing a 3 next to 7, which doesn't work, because one of those cells has to be 3. So 7 has to go here, which cannot be next to 3, so 2 goes there, 3 goes here. This is 1 or 2, based on, well, we already know it's not 3, so therefore, that's how you work it out. This is also 8 or 9, which means none of those digits are 8 or 9. But that digit could be 8 or 9, so that doesn't really help much. Well, this 2 means that's 1, so I guess that helps. This 2, 3 pair means that is now 1, so that's 2, which removes 2 from that cell, and from that cell. This 3, 4 means that this must be at least 8, because 7 is not 5 away from 3 or 4, so this must be at least 8, which means 7 must go here. Now this forms an 8, 9 pair, but what? No, it all works. If this is a 4, that's 9, but it could also be 3, making that an 8. So I guess we don't know. Actually, this 2, 3 means we know that that's an 8 now. So that's 9, this 8 means that's 9. This could still be 3 or 4, both of them are at least 5 away. So that's something. This 9 means that's 8, that's 9. This 9 means that's 8, that's 9. Again, both numbers work here. Both digits work. None of those digits can contain 9 anymore because of these 9s here. So at most they can take up 8, 7, and 6. And there's actually something special about those maximum values, because those maximum values add up to 21, right? How do you make 20 by altering those values? You need to decrease one of them by 1. How do you do that? You can't decrease 8 by 1 because you get 7 and that gives you repeated digits. You can't do the same for 7 because that gives you another 6, which gives you repeated digits. So the only way to decrease a digit by 1 is by decreasing 6 to make 5. And now actually we've proven that 5, 7, and 8 is the only possibility to go in this box. 7 here means none of those digits are 7, so 7 goes there. So 7 goes there. 8 means this must be 5, therefore that's 8. 9 can't be in those cells, so 9 goes here. Those digits are therefore 4 and 6, which we have not resolved. Fair enough. What else do we have? I mean, we have all those digits. Those digits do form pairs of some sort. 5 and 4 here. Here it's also 5 and 4. Oh, so that gives us more pairs down the columns. Which I guess kind of mean that 5 can't be in those cells. Can't be in those cells because of this 5. So 5 goes in those cells here. What does this mean for the 14 cage? I don't know. I mean, I can say that 1 doesn't go in the cage, but that doesn't really restrict anything, because the next minimum you can have is a 9. Like with 2, 3, and 4, you can have them add up to 9 at least. And that's way too far away from 14 to do anything useful with it. So I'm just staring for a bit. Ones are sort of useful. What about here? There isn't the same, no, that doesn't exist here. I mean, 2s maybe? Yeah, I can say 2 must go in the 10 cage. Oh, which does resolve everything, because 2 in the 10 cage requires you to have not 4 in it, because 2 with 4 makes your last digit another 4, which doesn't work, so it must be a 5. And therefore, with the 2 in the cage, 2 must be then accompanied by a 3 to make the remaining 5. We can resolve the 4, 5 pairs here. Now we know 5 is in the 11 cage, so those digits sum to 6 without using 1, 5. They must therefore be made of 2 and 4, which we can resolve. 2... 2's here. Yes, 2's must be here. So 2 in the 14 cage means those digits sum to 12. 5 is still valid because 5 can be with 7. You could also have 4, 8 in here, but you can't have 3, 9 because of the 3 there. Not super useful, no. Okay, we have a 2, 3 pair here. I mean, that digit is a 4, so that digit must now be a 5. In fact, here a 5 must also go there. This digit is now a 3 because of the 4 here. We have a triple down there, which has to be 7, 8, and 9. We know that digit can't be 9 because 9 would need to be paired with 3 to make 12, which doesn't work. Threes. Yes, 3's in this box. This 2, 3 pair sees that cell, so 3 must go there. 3 is in one of those cells. Can I figure out where? 2, 3 pair here means it's not there. But that doesn't really tell us much. Well, yes, we can do the same for the 2's, right? Because where does 2 go in this box? The 2 here sees those cells. This 2 actually sees that cell because it's in the same cage. This 2, 3 pair sees that cell, so 2 must go here. So, very cool. We found different ways to eliminate 2 from different cells. Those cells, I think 1, 4, and 6 to make the column. 4 can't be there. This could be anything. Yeah, we don't have much else to work with, I think. So let's look at... Well, I don't want to look at... I guess this 7, 8 means this has to be 4, 5 to make 12, to make 14. sorry, I was busy doing something. The ones here mean that one must go there. The last ones we're not quite sure. There are 3 of them, which form this interesting corner pattern here. But that is not going to do much for us. Right, okay, so where do 4 and 5 go in this column? 4 and 5 here mean none of those digits can be 4 and 5. Same for those digits. So this actually forms a 4-5 pair, because they must contain 4 and 5. Now those digits do form a triple, which have to be 6, 8, and 3. 3, 6, 8. Right, none of those digits can be 8, so 8 goes in the center. I think those digits form a triple of 4, 5, and 6. That digit can't be 4 or 5, so that digit is now 6. That digit is now 4 or 5. 6, 6. Can we figure out where 6 goes? Not entirely sure. No. This forms a triple. This must be 3, 4, or 6. It can only be 3 or 4 because of the 6 here. Now does that influence the 11 cage? I mean, not really, but we know this digit. Right, this must have a 1 in it, because the minimum you can have without a 1 is actually 5 and 6, which already add up to 11, which doesn't work, because we know 2, 3, and 4 are not in the cage. So 1 must go here. Those digits therefore sum to 10. If this is a 3, this must be a 7. If this is a 4, it must be a 6, which doesn't work. So this has to be 3 with 7. That resolves this 3, 6 pair, which resolves this 4, 6 pair, which still doesn't resolve this. Interesting. Okay, well, those 2 digits form a a pair of 8 and 9. 8, 9 pair. This 1 means that is no longer a 1. In fact, this 6 resolves everything. That's a 1, that's a 4. I say everything, I don't really mean everything. This is now 4, 5, and 6. 5 can't be in those cells. 5 has to go here. Did I say 4, 5, 6? I meant 5, 6, and 8. 8 can't be in that cell, so 8 goes here, 6 goes here. Those digits are 4 and 7. 4 can't be there, so that's 7. That's not 4. 4 is here. This can't be 7 now. So those digits are 5 and 6. This can't be 5. That's 6. That's 5. Those digits are, I think, 3, 8, 9 to finish the row. This can't be 3 because of that 3 there. So 3 must go here. 3 in the corner, which resolves this 2, 3 pair. It's always such a surprise to find a 3 in the corner, because I'm not really specifically looking for it. So I think it's quite funny when it shows up and I'm just taken by surprise a bit. Anyway, those digits are now, I think, 7, 8, and 9. But because of the 8 and 9 here, that digit is now a 7. This 8, 9 forms a pair, which means that last digit is a 6. Which should give us all the 6s in the boxes, except for the one here, which must go there. 8, 9 means this must be 8 or 9, but because of the 8 here, that is now 9, which hopefully resolves basically everything. 8 means that must not be 8, so that's 7. That's 8. Now this 2, 8 pair means that must now be a 4 to make 14. 5, this is now 4. That is now a 5. This 3 means that's 2, 3, 2, and we're almost done. Those last 2 digits are 1 and 7, which we can resolve. This is now a 7, that's a 1. Solving the puzzle in 17 minutes and 45 seconds. Actually, I did not expect to take this long, but hey, there you go. Solving the puzzle pretty quick for a 4 out of 10 puzzle. Yeah, I hope you enjoyed that puzzle. I'll see you next time. Bye bye. Hello, this is Blue Dog by James Sinclair. The second puzzle in his Artisanal Sudoku, volume 111. It is a fog of war puzzle, as you can see here. So there are a few puzzle elements in here that aren't actually shown. And so I guess we're just gonna look through the rules and I try and explain it as best as possible. Okay, normal Sudoku rules apply. So digits 1 to 9 in every row, every column, and every 3x3 box. Correctly entered digits will clear the fog around them. So if this digit was correct, then all the fog around it will clear to give you new stuff. Right. So we start off with, let's start off with the ones that we see here first. We have quadruple circles. So a digit inside a white circle must appear in one of the 4 cells around that circle. So we see a 4 here. So one of these digits must be a 4. we see like a 1 here, so one of these digits must be a 1, and so on and so forth. We also have those little black dots right here. Digits in cells separated by a black dot have a 1:2 ratio. So those cells, for example, are in a 1:2 ratio, meaning one is double the other. You could have something that looks like this to form your combination. Yeah, so there is one more thing here that isn't shown. It is a region sum line, which is it's traditionally a blue line. So for example, a region sum line could look like this, without that dot over there. And what we're saying is that along blue lines, digits have the same sum within each box the line enters. So for example, those 3 digits sum to the same as those 3 digits, which sum to the same as that digit over there. So yeah, those are all the rules. With that, let us begin solving. Alright, so the first thing I see is, we have to work with this because there's no else to work with. And I notice that 3 of those cells are touched by a black dot, that cell is not. So where does 7 go in this quadruple? Well, it can't go in any of those cells because 7 does not have a partner. And in fact, a black dot can only have 4 possible combinations. They are 1, 2, 2, 4, 4, 8, and 3, 6. And since we know 7 is not in any of those cells, we can put a 7 in here. We start having a blue line. Alright. Other digits that cannot be next to a blue dot are also 5 and 9. They also do not have anything you can put beside them. So yes, here we now have 1, 4, and 6 in these cells. The 1 can't be here because the only thing next to 1 is a 2. And so both of those cells will have to be a 2, which don't work. So similarly, 6 can't be here because both of those cells would then have to be a 3, which doesn't work. So this digit must be a 4, which must be next to 2 and 8. Those are the only things that can go next to the 4. 1 must be next to 2, so 2 is in one of those digits, and 6 must be next to 3, so 3 is one of those digits. Right, and now this digit must be an 8, because this digit sums to the same as those digits, which sums to the same as those digits. And so, you can't put a 2 here because you can't make those digits sum to 2. You can't use 2 1s, that just doesn't work. So this digit must be an 8. That digit is therefore a 2, giving us a 3 here, which must be next to 6, which resolves everything. So lots of digits already, nice. This 8 here means those sum to 8, which means that digit must be 6. Those digits sum to 8 as well. Right, and if there is 8 in there, you must have a 1. Because without a 1, you are summing at least 2, 3, and 4, which have to be 9 at least. So there must be a 1 in here somewhere, and because of this 1, the 1 can only be in one of those cells. Cool, what's next? Well, very interestingly, this quadruple contains a 3 and a 7, and it's very cool because, yeah, that's weird, because quadruples can only display digits in increasing order. So, I don't think it's required, but I think we do know that one of those digits here has to be between 3 and 7. Of course, a more logical deduction to make is that 3 here means none of those digits can be 3, so the only 3 in this quadruple has to be here. The 7 now come in those cells, so 7 must be here. And those digits are therefore 5 and 8. And I don't know what those are because the line actually touches 4 cells in these boxes, so those could be as high as they want to be. But it can't be 7, 5. Right, because let's look at those cells here. What do those cells contain? Well, those cells at least contain 1, 3, 5, and 6, because they cannot contain 2 and 4, which already adds up to 5, 6, which already adds up to 15, which means that this definitely can't be as low as a 12, because this is at least 15. So this must be an 8, which is in fact 15, which means that this actually has to be the minimum, and therefore has to be 1, 3, 5, 6. 1 and 6 can't be there, giving us a 3, 5 here. Oh, I can see, this is the dog's head, right? Yeah, it does look like a dog, so that's why it's called Blue Dog. It's a dog made of blue lines. Awesome. Well, those digits also form a pair. I think they have to be 2 and 9. Sorry, no, 7 and 9. 2 is already there. 7 can't be here, so that's 9. That's 2. No, sorry, that's 7. I don't know what I'm saying. But Alright, this means, right, the 3 here means those cells can be 3, so 3 must go there, which gives us a 5 here. That can be 3 or 5. In fact, that can be 5 either. Those cells must therefore be 1 and 7, which does something maybe. Right, okay, so let's take a look at this now. That digit must be the same as that digit because they have the same sum and they are single digits, so that's just 8. And those digits must have a 1 in them somewhere. We don't know where, but it must have a 1 in them somewhere, for the same reason as a 1 here. Alright. So now what? I'll probably do Sudoku maybe? Not really. Maybe we look at those digits. Those we know are all part of the region sum line. The only thing that we don't know is how long is this line, because the line could theoretically extend this way, or it could extend this way, or it could just stop here, and we wouldn't know because of the fog. Whoa. So what then? Maybe we could do something here. Right, because 1 must be in here, the remaining digits must sum to 7. And there's a 3 in here. So the only way to make 7 without using a 1 or a 3 has to be 2 and 5. So those digits have to be 1, 2, and 5. Which means those digits are 4 and 9. 4 can be here, so that's 9. That's 4. Does that help with anything? 2 can be there. 5 can be here. Not really. No. Okay, what about those digits? Right, again, because of these 3's, 3 can't be in here. So by the exact same logic, this has to be 1, 2, and 5. This can be 1 or 2, so that's now 5. 5 can be there, so 5 goes here. Those digits can't have 5 in them, so they form a 1, 2 pair. There is also a 1, 2 pair over here, meaning the last 3 digits in here have to be 6, 8, and 9. 8 can be in those cells, so 8 goes here. Those digits are therefore 6 and 9. Nice. Right, that's 15. Which means this can't be as high as a 9 then. Right, because if this was a 9, then those sum to 12, those have to sum to at least 3, at most 3, sorry, to make 15. They could sum to less than 3, but obviously they can't because you can't make 3 in 3 cells or more. So those digits have to sum to a 3, but can't be 1 and 2 because there is a 1, 2 here. So if you made this 1, 2, then this has no option, which means that this can't sum to 3, which means this can't be 9, so this must be 6. That's 9. And in fact, those are the only 2 digits summing to 15. Sorry, no, those 4 digits sum to 15, those sum to 9, therefore those sum to 6. Without a 5 must therefore be 2 and 4, because 1 and 5 is not available. This 2, 4 pair sees that cell, so that's 1, which resolves this entire set. This, the 1, 6 here means that must be 3. Cool. I think we can put that digit in. That must be a 9 to complete the row. We have a pair there of 1 and 7. We have a triple here of 6. 3, 4, and 6, sorry. That can be 6. Now that digit is in a ratio of 1 to 2 with that digit. And I think the answer this must be a 4 next to 8 because it can't be 2. If it was 2, this digit would have to be 1 or 4, but both are not possible. So this must be 4, which must now be next to 8 because it can't be next to 2. So there you go. That's 2. And so this gives us 15. 8 here means those digits sum to 7. Or it could also be those digits summing to 7. So I guess we're not entirely sure. Yeah, because your line could look like this if it wanted to. Right, well, those digits, there we go. They have to sum to 15, but can't have a 9 in them. So they must be made of 7, 8. They can't be made of 6 and 9. 7, 8 resolves this 1, 7 pair, which does give us this here. So we do know those sum to 7 now. The 1 means you can't use 1, 6. The 2 means you can't use 2, 5. So this must be 3 and 4. The 3 here means that's 4, that's 3. Awesome. Alright, this is a very long region sum line. 1 here resolves this 1, 6 pair. Does that resolve anything up here? I don't think so. That's fine. This is 3, 7, and 9. 3 come in those cells, so 3 goes there. That now can't be 3. This is a 7, 9 pair, which we can resolve. 9 goes here, 7 goes here. Those digits now form a triple, which are 2, 5, and 6. Sorry, 2 come in those cells, so 2 goes there. 5 here resolves the remaining 5 and 6. And those digits are 4 and 9. So 9 here resolves this. 4, 9, this 4 makes that a 6, which leaves you a 3, 4 pair. So that's unfortunate, I guess. This must be a 5 to finish the box, which goes into here and does double. Wow. Okay. I mean, there's a pair, there's a triple over here, and actually a pair over here, which we might look at first. These are 6 and 4. What about the triple here? 1, 2, and 7. But this can't be 7. Those digits are 1, 8, and 9. And therefore those digits are 2, 5, 7. So that can be 7. Okay. Well, I guess we know that those digits are all part of 15 at the very least, which might be able to help us here. Yeah, this one has to be a 1. If it was any larger than 1, it would have to be 8 or 9. But if we took the smallest it can be, that is not 1, 8. This is, oh, this could be 4, right? Yeah, wait, hold on. Hold on here. Now those, oh, I was like, I mean, this line could extend. It could do weird movement, and technically we wouldn't know. So we are unallowed to guess any strange things it does. Yeah, if this is a 9, 9 could be with 4 and 2 to make 15, that's fine. 8. Well, 8 is a bit stranger, because 8 with 6 gives you 14. That digit can't be anything to make 15. Anything you put there would increase above 15, so 8 with 6 doesn't work. 8 with 4 gives you 12. That digit could now be a 2, but it would need a 1 to make 15. It would need one more, but it could end up here with a 1, right? Okay. That's fair. I guess we don't know. We could do other stuff maybe. Right, this 7 resolves this 8, 7 pair. So I guess we should have looked at that first. We have another pair over here, I think. 2 and 4. 2, 4 pair. Right, I guess those digits under 15, we could use that as well. Right, 7 resolves this 1, 7 pair, which does give us some stuff to work with. This must be 5, 8, and 9. Oh, that's very good, because those digits, yeah, those digits have to just be 5 and 8. And we'll see why later. Let me just fill in these in first. This is 1, 3, and 6. This can't be 3. But those digits are at least 13 if you use a 5 and 8, which is the smallest. So these are at least 13. In fact, if you took the smallest numbers here, you would have 2, 5, and 8, which do add to 15. So they must be as small as possible. They must be 5, 8, and 2. The other way to think about it is, if you made this any bigger, you need 5, 9, which is 14. And 14 doesn't have a 1 here to accompany it. 8, 9 here is 17, and 17 is way over 15, which doesn't work. So this must just be 5, 9 with a 2 here. This 4 resolves this 4, 6 pair. And now we know that, well, an 8 here doesn't work, right? Now I said an 8 here needs a 2 and a 1. But this line here never hits a 1. It goes into here. It can't reach here because the line doesn't show up there. This doesn't have a 1 in it. Going out of the box would put you into a new sum. So I'm pretty sure this can't be 8. Is there any easier way to figure that out? 6 here removes a 6 from that cell. This must be a 9. 9 removes a 9 from that cell. 9 could have a 2 here. Sorry, wait, what does 1 have? Well, 1 with 4 gives you 5. You need 10, right? Yeah, how do you make 10? It doesn't work either. So I guess we might have to just look at each case. We saw just now that 8 didn't work. and my reasoning was there, but I wasn't quite sure if that was what they wanted me to do. The 1 here also doesn't work for very similar reasoning, where if you reached 1 here, the remaining digits in this box on the line have to sum to 10. But even if you selected those two, you can't have a set that sums to 10, and you can't go in here, you can't go out, which means that this can't be 1, I think. So this must just be 9, which must be next to 2. Okay, so that does something. Again, not very sure if that's intended, but I guess we made it through. This 1 means that's 6. We have 1 3 pair here. I guess we have to resolve everything else. My instincts tell me that the line looks like this, but it could very well look... Yeah, no, it has to, right? It has to. Because this has to extend here, this has to extend here. There is a very small chance that your line branches. I don't know if this is allowed in making puzzles. I'm not going to take the risk, and I'm going to assume this is a possibility. So let's not think about that. Let's do what actually should be done. This 1 means that's a 2. This 7 means that's a 1, therefore that's 2. Wait, sorry, that's 7. Whoopsies. 1 means that's 3, that's 1. And this line is in fact what we see it as, which should give us the remaining digits. Those are 4 and 9 resolvable. 4 9 9 4 means that's 3 4, which is weird because this should completely resolve, right? Yeah, we don't actually need the line or the dot. This just resolves. Huh, that's really weird. Okay, well, I don't know what it is, but 6 and 8. This is 8. That's 6. And those digits are 3 and 5. 5 goes here, 3 goes there. Solving the puzzle in 15 minutes and 59 seconds. Awesome. Alright, so let's look at the puzzle title again. Blue dot. I definitely see a dog's head here. Is this the body of the dog? Or is this another dog head? It could be. I don't know. It's like one of those tests where they tell you which direction the dog is facing, and I guess both work. And I guess this clue might just be there to patch up continuity, so it actually looks like a real dog. Yeah. Well, that's fun. I hope you enjoyed this puzzle. I'll see you next time. Bye bye. Hello, this is Confiable by James Sinclair, the third puzzle in his Artisanal Sudoku, volume 111. So yeah, it is the hardest one in out of all the free puzzles, so let's take a good look at it. Normal Sudoku rules apply, and all clues are standard, so digits 1 to 9 every row, every column, and every 3x3 box. Whoa. Killer cages, so we have some cages here. Digits, sum of digits inside each cage is equal to the small number in the top left corner, so those digits sum to 20 for example, those digits sum to 16, and same for the rest of the cages. Okay, next. Arrows. The sum of the digits along an arrow is equal to the digit in the connected circle. So, for example, digits here have to sum to whatever's in there, digits here have to sum to whatever's in there, and so on. Lastly, we have a black dot here. Digits separated by a black dot have a 1 to 2 ratio. So one digit is double the other. For example, 3 and 6, that works. Yeah, that was really quick. Wow. Yeah, with that, let us begin solving. Right, so this one is a tough one, so I think we might have to spend a bit more time on this. But what do we have here? Well, let's start with the biggest cage, the 22 cage. Yeah, because arrows are pointing into it, which might tell us something about those digits. Those digits can't be that high, right? They can't be as high as 9. They could be 8 and 7. I see. I think I see. Right. Those this can't be a 987 triple. Because of the 9, if it was a 987 triple, 9 will have to be here. And where does 8 go? Wherever 8 goes, you can't put a 9 on this on this circle here because of the 9 already in the cage. And the same goes for this 8. You can't put a 9 there. So 8 doesn't have anywhere to go. And so it can't have both 9 and 8 in it, I think. There might be a lot more... Oh, there might be a lot more to do with this cage than I thought though. Right, let's start with the 22. It must have a 9 in it, because without a 9, the maximum you can have is 6, 7, and 8. Those sum to 21 only. So without a 9, you can't reach as high as 22. So there must be a 9 in here, which must be there. Now those digits therefore cannot have an 8. Because, yeah, if there's an 8, whereas this digit can't be anything, it can't be higher than 8, but it also can't be lower than 8, because you can't have anything here that causes these two to sum to like 7 or something. So 8 can't be on that arrow, which means that those arrows sum to a maximum of 6 and 7, which is 22. Right, so there you go. This must be 6 and 7, which sum to 22. Therefore, what does that say about the circles outside? The 6 and 7, the 9s, and the 22. I forgot to explicitly mention that. So what happens to the circles outside? Right, well, because there can't be a 9 in the circle, and those are 6 and 7, each of these must be must be 7 and 8. Because they must be at least 6 plus 1, and they must be at most 7 plus 1. So this digit now is 1 or 2, right? Yes, it's 1 or 2. Because it can't be as high as 3. Same here? Yeah, same here. Okay. Or we might have something here then, I guess. Those digits form a quadruple of some sort. What if those were the same digit? Well, that means that none of those digits have to be 8, right? Yeah, in fact, they were the same digit. If they were the same digit, they would have to be 8, because one of these digits are 7, so they can't both be 7, because you wouldn't have anywhere to put a 7 in here. So those digits, if they were the same, would have to be 8, which look at all of those cells. Which means that digit, which means 8 must be in here in that case. I think that's possible though, because you could have 8 with 1, 2, and 3 to make 14. And then your 8 can pair with 1 to make 9, your 2 and 3 can pair together to make 5. So that's fine. What about this cell? This cell is pointed at by this. Same for this one. In fact, this is... yeah, all of these are all diagonally symmetric, so we really only need to look at one of them to work. Even the totals are symmetric. Well, we definitely know those digits can't be 9. There's a lot of things you could do though. If this was a 7, 8 here, you could have this just be a 6, and then those will sum to 10, which is fine. Yeah, that's fine. I guess whatever digit shows up here won't be in here at all. Again, it still could be fine though. You could have something like 6 with 1, 5, and then 4, 6 here. Yeah, that looks fine, and I think there's way more different combinations you'd have. Okay, so fair enough. What else do we have? I wanna look back at what if those digits were the same again. They would have to be here. But we already saw that 8 in here is fine, right? You could have something like this, and then you could have this. I think that's fine. I guess one thing we could note is that what are those two digits? Because those two digits completely fill this box, we know those digits have to therefore sum to 14. And well, they can't both be 7, right? Yeah, because if they were both 7, then 7 in this box must now be on its own arrow, which doesn't work. So they can't both be 7, therefore they're either 5 and 9 or 6 and 8. They can't be the same, therefore, what I'm saying. I mean, if it was 6, 8, then we know that this can't both be 8 then. Whatever digit is in here can't be in that cell, can't be... I guess it can't be here, but it could be on the other arrow, I think. Because 5 could be, 5 is next to 9, right? This could be 4 and 5. This could be 2, 3, that's fine. What about a high digit? I guess the high digit is what's important then. Because the high digit is always paired with a lower digit. Right, the 8 is always with a 6, the 9 is always with a 5. Yeah, and therefore what that means is, I guess the high digit must be... If this is the higher digit, then it can't be on its own arrow, it can't be on the lower digit's arrow, it can't be in those cells. That higher digit would have to be here. There you go, which now sees both of those cells. And is it the same here? Yes, it is the exact same. Right, so let's look at the higher digit here. We can say, in case 1, that is a high digit. Higher digit now can't be here. We know that digit will always be lower, and therefore cannot be on the lower digit's arrow. Because whatever this is, you can't put a higher number here. And therefore this digit would have to be in here somewhere. Now wherever it is, it would see both of those cells. And therefore, that high digit, if it was here, can't be an 8. Because both of those can't both be 7, otherwise you'd have no 7s in here. And the exact same thing happens if it was this that was a higher digit. Now, there can't be a high digit on its own arrow, the high digit can't be in the lower digit's arrow, the high digit can't be here, and the high digit has to therefore be here, which now again sees both of those arrows. So that's pretty cool geometry, which is to say that none of those digits can have an 8 in it, because that would force these digits to both be not 8, which isn't possible. Which means those digits have to in fact be 5 and 9. And therefore the 9, well, we don't know what the 9 is, but if this is the 9, we know 9 is in here. If this is the 9, we know 9 is in here. Right, which therefore means that 9 isn't here, 9 isn't there. Or sorry, 9 isn't here and 9 isn't there. Ooh, yeah. Right, we know that the high digit always sees those cells, firstly. So let's mark those down. The 9 actually also sees those cells. So none of those digits are 9s. Those digits are also not 9. So 9 must be in the 16 cage somehow. And 9 can't be on the arrow because nothing here can be bigger than 9. So 9, I guess, is in one of those cells, which is pretty cool. I'm gonna remove the color here now. But I guess 9... there you go. The 9 in the 16 cage must be paired with a 7. And you need 3 digits that sum to 7. The only way to do that is with 1, 2, and 4. That's cool. This must be 1, 2, 4, and 9. The same goes for here. This must be 1, 2, 4, and 9. And we know 9 cannot be on the arrow, so let's remove those. Actually, yeah, because those digits only have a few possible combinations, you can only make 3 different permutations of those digits. 1, 2, 1, 4, and 2, 4. Actually, in math, they're called combinations, right? Not permutations, because permutations allow for different orders as well. That's why it doesn't talk about order. So this is either 1, 2, 1, 4, or 2, 4, which sum to 3, 5, and 6 respectively. So there are our options. Right. Alright, this is actually really good progress, I think. I hope it's really good progress. I don't actually know. Well, I can say that those digits must have a 4 in them somewhere, which gives us sort of an X-wing on both of these blocks here, because those must also have 4 in them, which is to say that, yes. So, let's talk about X-wings. Those two columns must have two 4s in them, right? Because there is one 4 in each column. There is one 4 here, and there is one 4 here. So where does the 4, which actually means that those two 4s take up both 4s in the columns, which means that nowhere else in the two columns can there be a 4, which then implies that 4 must be in one of those cells in this box. Another way to think about it is, where does 4 go in this column? There's a 4 here, which means none of those cells are 4, none of those cells are 4, so 4 goes there. And the same logic applies here, 4 goes there. Right. So now what? I don't know what that means now, but let's see. How could we figure out the 5 maybe? Does the 5 do anything special here? We know the 9 did something special. The 5? 5 can't be on its own arrow. It could be on the bigger digits arrow though. See, that's the problem. So 5 now has like 4 options in this case, and in this case would have 4 options here as well. I don't know. Alright. Well, maybe let's look at those. Yeah, this digit can't be in those cells. And we know 3, 5, and 6 aren't in those cells either. So I guess this digit has to be in here somewhere. Which, in this box, or they could be in here. They could be in here. So I think that doesn't really tell us anything. Same for this here. Could be in one of those cells. Yeah, alright, there's nothing there. There could be still. I mean, maybe now if they were the same digit that does something. If they were the same digit, then none of those cells can be that digit. So that digit must be in the cage somewhere. I mean, okay, if they were the same digit, they also look into those cells, which means that digit must be in those cells somewhere. I don't know what it means though. Maybe we should talk about how the 5 and the 9 work together. Like, 5 could be made with 1, 4 or 2, 3. Does that hinder the 9 in any way? Well, the 9, if it was 1, 4, then the 9 could be made with 2, 7 or 3, 6. If it was 2, 3, it could be made with 1, 8 or 4, 5. And I think all of them are fine. Yeah, in fact, could those digits... Maybe can those digits have a 4 in them? Do those digits have to have a 4 in them, is what I'm saying. If they didn't have a 4 in them, then the 5 is made of 2 and 3. Yeah, it could be 2, 3, 1, 8. Yeah, you don't have to have a 4 in it. Because if it did have a 4 in it, then we can do a lot of things with this having a 4 in it as well. Does it have to have a 1 in it? No, because 2, 3, 4, 5 adds to 14. So without a 1, you could still make it 2, 3, 4, 5. I mean, I guess that would be kind of cool though. Because 2, 3, 4, 5 forms a bunch of X-wings with the 2s and the 4s here, which gives you 2, 4 pairs in those cells, which is kind of awesome. But that isn't confirmed either. If there was a 1, the same thing kind of applies, where you have to have a 1 X-wing here and here. So 1 is in one of those cells. If I said 4 has to be here, then the 4s here would form their own X-wings on themselves and say that none of those digits are 4, which puts 4 here. Which is also really cool. But again, we don't know. It's possible to not have a 4 in there. Maybe it's time to look at this cage. The 20 cage doesn't have to have a 9 in it. It could be 8, 7, 5, which adds up to 20. Yeah, this is kind of whack. It's very weird, but I feel like there's a lot of synergy here. You could have no 1 in here, you could have no 2 in here, you could have no 4 in here. But you can't have like multiple of them be missing at once. Like if you didn't have 1 and 2, then the 3, 4, 5 and 6 remain. You can put 3, 4, 5, 6 in, but that's way too big. If you didn't have 1 and 4, then 2, 3, 5, 6 gives you way too big of a number as well. If you didn't have a 2 and a 4, if you didn't have 2 and 4, if you didn't have 2 and 4, then the digits you can put there are 1, 3, 5, 6, which add up to 15, which is also too big. Right, so you can't even have 2 of them missing. You can have 1 of them missing, you can't have 2 of them missing. And therefore, in this cage, there will always be 2 out of the 3, 1, 2, and 4. So it either has 1 and 2 in it, either has 2 or 4 in it, or either has 1 and 4 in it. And in all 3 of those cases, form X-wings in those cells. So let's go through a very quick example of saying, well, what if there were a 1 and 2 in here? Well, then the 1 and 2, where does 1 and 2 go in here? It can't be in those cells, it can't be in those cells. 1 and 2 forms a pair there. If it were 1 and 4, the same applies. 1 and 4 can't be there, can't be there. This forms a 1-4 pair here. If 2 and 4 were in here, same applies. 2 and 4 come in those cells, 2 and 4 must be here. And we have proven that you cannot have 2 of them missing. So at all times, you must have at least 2 out of these 3 values. And in fact, you can't have 3 of them. You can't have all 3 of them. Because if you have all 3 of them, then you have to fit all 1, 2, and 4 into these 3 cells. Which doesn't work. Wow, okay, so what that means is that those cells are either going to be 1, 2, or 4 at all times. That's crazy. I did not expect that to be something. But yeah, those digits have to be 1, 2, or 4. Because in any case you put here, they will form an X-wing, which causes those 2 digits to be whatever 2 digits you place in here. That's crazy. I mean, does that help? It might. It gives us a lot more options. And we know that they have to be the same combination. Both of these are the same combination of digits. Like if this is 1, 4, this is also 1, 4. I don't know how that does anything though. Yeah, once again, I'm inclined to look at the 20 cage. I still don't know how that works. You could have a 9 in it. You could have no 9 in it. I guess what you could say is that this can no longer be made of any combination of those digits. So they can't be 3, 5, or 6. They can't sum to 3, 5, or 6. Because if this it could still sum to 6, so you could have 6. You could have like a 6 with a 1, 5 here, which makes this a 2, 4 pair. That's possible, isn't it? And then 5 could be with 2, 3, the 1, 4 pair. Yeah, so okay. I guess we don't really know. We just know it can't be 3. Because 3 needs 1, 2, and then 1, 2 here means those digits can't be anything. Hey, wait a minute. Oh, sorry, no, I was blanking out. I was like, hey, wait a minute. 9 can't be in those cells. Whichever 9 goes, that has to be in here. Does that help? Not really. Yeah, because we already have the 9s in one of those cells. And then 9 can be here somewhere. I guess 9 is in one of those cells. If this was a 9. If this was the 9, then it's in one of those cells. No, it doesn't do anything. I mean, 9's always in one of those 5 cells. Because it isn't anywhere there. Oh, wait, hold on. Let's see. 7. 7 can't go in here. If 7 was in here, it would need 1, 2, and 4. And we already know that you can't have all 3 digits in here because that forms an X-wing with all 3 of those digits, which forces all 3 digits to be in here, which doesn't work. So 7 can't be in here. Which means 7 is on the outside. Have we proven that those are both... No, those could both still be 8. So 7 could be here. But I guess we've proven that 7 is on the outside. What does that mean? I think it means literally nothing. Oh, wait, hold on. One of those digits are 7. Whichever digit is 7 looks into the box next to it and says 7 goes in one of those cells, which then goes in one of those cells, which does something. And then the same is for this. Oh, so 7 can't be here. Wait, no, could 7 be there? If 7 is here, both of these are 8. And then one of these would be 7, whichever it is, completely has no option. So 7 can't be here. I guess you could still then say that 7 is one of those cells, although I don't get how that's useful in the slightest. What else can we eliminate from here? I don't know what else we can eliminate. I guess we'll mark those since we are doing that. Oh, the 7. Yeah, none of these can be 7. If 7 was here, then 7 is one of those cells, which means that 7 now has been one of those cells. And now, because 7 is in those cells, none of those can be 7. And diagonally, symmetrically, we can say that this can't be 7 because one of those are 7. Therefore, 7 is one of those cells. And now, this and whatever's in here, we'll see both of those cells, so none of them can be 7. Cool, so I guess that means that these are both 8. Which gives us a lot, because we now know 8 come in those cells, 8 must be in here, and must therefore be accompanied by 1, 2, and 3. Sweet. Which now means that we form the 1, 2 X-wing, which means that those digits are all 1 and 2. Again, it still works, whichever way we want it to work. But I guess we have a 1, 2 pair there now. Which could mean something. Yeah, those digits are now at least 3 and 4, which means those digits are at least 7. What else do we have? I don't know. But that digit now can't be 5 or 9, because 5 and 9 here would eliminate 5 and 9 from both of these cells, which doesn't work. So I think that digit has like 3 options. It can't be 1, 2, 3, 5, 8, or 9, so it's 4, 6, or 7. Which doesn't say much, but I guess it's something. Let's see, one of those digits, they can't both be the same. So 9 could be made of 4, 5, I guess. Yeah, 9 could be made of 4, 5. They could also be made of 3, 6. They can't be made of 1, 8, or 2, 7. But they could be made of 4, 5, or 3, 6. Then the 7 is made of 3, 4, which is fine. The 8 is made of 3, 5 because it can't be made of 1, 6, 2, 1, 7, 2, 2, 6, or 4, 4. So it must be 3, 5. What does that mean? Maybe it says something about the 20 cage. Yeah, it does. It definitely does. Yeah, it definitely says something about the 20 cage. There you go. It says that those digits add up to at least 35. because if you had those be as small as possible, they'll have to be 7, 8. 20 with the 7 and 8 here means this is at least 25 if you made it as small as possible. But what that also means is that those 5 cells are at least 35. But what do 5 cells sum to at most? If you took 9, 8, 7, 6, 5, they sum to 35. So those cells we know sum to at least 35 because of the clues. But because they cannot repeat, they sum to at most 35, and therefore must sum to exactly 35. So those digits must sum to 15, which can only be made of 7 and 8. Right, there you go. So those digits must all have 3 in them. They're either 3, 5 or 3, 4. And we don't know which. But those digits now are the remaining digits from 5 to 9, which have to be 5, 6, and 9. This cannot be 5 or 9 because those digits have to have a ratio 1 to 2, and we know that 5 and 9 have no partners in this scenario. So that's 6, giving us our next 2 digits. 6 can only be next to 3, so I guess that's that. So 5, 9 pair here. Those digits are 1, 2, and 4, which might do something. Alright. Now what? 6. Now, well, where does 6 go? 6 can't go in here because 6 with 3 gives you 9. So 6 can't go in here. 6 must be in one of those cells, which means that 6 has to be in one of those cells, which means that digit is not 6. Which means it has to have a 2 in it, I think. Because, no, sorry. It has to have a 1 in it. It's either 1, 2 or 1, 4. So there you go. This has to have a 1 in it. Sure. That works out. What else do we have? 3 is in one of those cells, which could be anything. It could be 3 here, it could be a 3 somewhere else. I mean, I guess I can mark those 3, 4, 5. It doesn't really help much because it isn't very confirmed yet. 3, 4, and 5, but maybe that does something. Right, one of them are 3, 5, right? Yes, one of them has to be 3, 5. But this one can't be 3, 5 because there's a 5 in one of those cells, which will always see both of those cells. So 3, 5 has to be here, which means this has to be 8, that has to be 7. This must therefore be 3, 4. The 3, 5 here resolves this 5, 9 pair. Give us more digits. The 5 here also resolves this 5, 9 pair. This must be 9, that must be 5. We know in here 8 can only be with 9, so this must have an 8 in it, which is next to 1. The remaining digits 2 and 5 go in the 5 arrow. 1 is removed from those cells, 2 is removed from those cells. This could still be anything, I think. Awesome. 3, 4 resolves this 3, 4 pair, so this is now 4 over here. I mean, those digits. 8 is in one of those cells. 8 is in one of those cells, which means in this box, 8 is in one of those cells, which forms a 6, 8 pair. This digit is therefore 1 or 2 to finish up the column, which forms its own pair over here, so that's awesome. 5 resolves this 3, 5 pair. So we know this is now a 1, 2, which gives us a 4, 9 here. Okay, what next? 4 means that is not 4. This 1, 2 pair gives us a triple at the end, which must be 5, 6, and 7. So 3 is in one of those cells, I guess. We don't know where it is, but it's there, it's there. Oh, sorry, this 2, 3 pair sees that, so that's a 4, that's a 3. This 4 means that's 1. So that's 9, so that's not 9. So now this 1 means this is either 3 or 5 again. This 1 resolves this 1, 2 pair, that's 1. This 2 means that's 6, so that's 7, so that's 1. This 1 resolves this 1, 2 pair, which means this is 2. Okay, we should be close, I think. This 1 means this 1, 2 pair is resolved. This 1 resolves this 1, 8 over here. This 2 resolves this 2, 3 over here. This 3 resolves this 3, 5. Therefore that can't be 5. Oh, that's it. Aww. Okay. Oh yeah, 4 in this column. This 4 here and wherever the 4 is here would see those cells. Wherever the 4 is here would see those cells, so 4 must be here. Another way to think about it is if 4 was in here at all, that would form an X-wing here, which doesn't work. Oh, sorry, no, wherever the 4 is here will form an X-wing with this, which means 4 isn't in any of those cells, which doesn't work. But that's a really dumb way of saying it. So I guess 4 is just there. Nice. What else do we have? Eight must be here. Those digits are 6, 7, 9. Sorry, it took me a while to figure that out. Don't know why. This can't be 6. 8. Sorry, 8 is already there. What digit is missing here then? Is it a 2? Yeah, 2 in this column can't be here, so 2 must be there. I think we can finish up most of the stuff already, right? Yeah, this 2 resolves this 2 4 pair. Don't know why I didn't see that. Which means that 2 is one of those cells forming a 2 4 pair. Nice. Those digits are triple, therefore. Triple with 3, 5, and 6. 3 can't be any of those cells, so 3 must be here. I guess this 1 2 pair would have told us as well. Those digits are therefore 3 and 7. Therefore, those digits are 6 and 9. Nice. Those digits are therefore... Wow, there's a lot of pairs today. 7 and 5. Cool. Those digits therefore actually do form a pair as well. I think they have to be 3 and 6. This therefore can't be 6, that's 7. This therefore can't be 5, or can't be 6 or 7, that's 5. Yeah, that gives us a lot of stuff. 7 in this box has to be here. The remaining digits are 4, 6, and 8. We can't do anything with that, I think. It's just barely unresolved. Yeah. Alright, well that's fine. 6, 7, 9 means this has to be 6, 7, or 9. Whoa, what did I do? 6, 8 means this can't be 6. In fact, this also forms a triple, I think. It's 5, 7, and 9. 7 means this can't be 7. What else do we have? I don't think we have a lot more easy Sudoku to do. 4 means those digits can't be 4. Yeah, I think I'm a little blind at this point. What am I looking at? It's too many pencil marks. Way too many pencil marks for me to notice any of them for real. This is definitely just regular Sudoku though, because every clue has been resolved already. Maybe we just look at other stuff. Yeah, like in this row, this digit is either 1, 2, 4, or 7, but can't be 1, 2, or 4. So that's just 7, which resolves this 3, 7 over here. Those digits now can't be 3, which means those digits can't be 5 or 8, because there's a pair over here. Those digits therefore form another pair, which is 6 and 9 as well. That is resolvable. 6 means that's 4. In fact, this can't be 6 either, so that's 8. 6 goes up here. 4 resolves this 1, 4 pair. 4 here resolves this 2, 4 pair, which resolves this 1, 2 pair. 1 must go there. This must be 5 and 8. 8 here resolves that. We have a lot of stuff that we can do after this, I think. Yeah, 6 resolves this 6, 9 pair. Nice. This 9 resolves this 4, 9 pair. 4 resolves this 3, 4 pair, which resolves this 3, 6 pair. And we are on a roll, actually. 6 resolves this 6, 8 pair. 8 resolves this 5, 8 pair. Now this 5 means that's a 9, that's a 7, that's a 5. This 5, 9 means that's now 7. And our last round of eliminating 7 resolves this 5, 7 pair. 5 resolves this 5, 6 pair. And that resolves this 6, 9 pair, which gives us all our digits, solving the puzzle in 40 minutes and 57 seconds. Awesome. I really like the logic with this one. The one where you look at the pairs kind of crossing each other here and forcing stuff into here. That was very cool. Yeah, I like that. Well, I hope you enjoyed that puzzle too, just like I did. Alright, I'll see you next time. Bye bye.